Welcome to this bootcamp. If you can hear me, please can you use your maybe use your favorite reaction. So let me see if you can hear me. Mic check. All right. Okay, that's good. That's good. All right. So welcome back to the bootcamp. As you already know, I'm Gideon, one of the co-organizers for GG Ajah. So today is week 8. We are going to be having certain algorithm, and it's going to be taken by no other person but our wonderful lecturer, tutor, ambassador, and other things, right? So it's going to be taking us Oluwaseyi Bello, a software engineer at Google. So I'll be handing over the mic to him now. But before that, let's just have some ground rules. First off, if you want to ask question, don't unmute your mic. Just drop the question in the comment section. It will be attended to. You're only permitted to unmute your mic when you're specifically being called upon to do that, right? And also, we just want a very quiet room, no very quiet room, like I said, and other rules might be communicated later. All right, thank you very much. I hand the mic over to Shay. Yeah, thank you.
Thanks for that introduction. So welcome everybody. Today we are going to be discussing sorting algorithms, and let me share my screen. Okay, so just to add to the ground rules that have been said earlier, usually after the session, there's a feedback form that goes out. We use that to gather data as to how folks are receiving the session. So please take some time to fill that out. Any type of feedback, good feedback, bad feedback, neutral feedback. It helps, as an instructor, it helps me understand areas we can improve. And it's also beneficial to you as well because we are able to improve the curriculum as we go forward. So with that being said, let me start the slideshow here. I don't want to take too much of our time because we have a lot to cover today. We are going to be covering certain algorithms and we have a long way to go. And today, I'm mainly going to be doing a lot of visualization. I'm going to be doing a lot of demonstration with visualization. I think that's the best way for folks to. Oh, my bad. I didn't ask if I was heard. Can everybody hear me? Okay, good. I should have confirmed that first. Okay, so let's start. So we are discussing sorting algorithms, and so coming up with this, it's kind of difficult as to how to come up with ways to teach sorting algorithms because they're just algorithms, right? But the major thing I'm trying to achieve here with folks is I want to build your intuition, and I want you to be able to look at sorting algorithms and be able to know different problem-solving strategies from there. So we are going to be going over the big picture of what we've been doing, just to ensure that we're all on the same page and we know what we are learning today, where we are learning it, where it fits in the whole computing systems hierarchy. Then we'll talk about sorting. What is sorting? Why do we sort? Why is it important? Then I will not be going directly to sorting algorithms. I will be using algorithmic design strategies to explain them. So every sorting algorithm has like a design strategy behind it. And most times when you read or when you look at certain algorithm, they just give you the algorithm. They don't really tell you what is the intuition behind it and what design strategy they're using. So some of these might be information you find out there, some of them might not be, but that doesn't really matter. What's important is to understand how the sorting algorithms work. Then, so we're going to start with brute force. Then we'll go to the strategies, decrease and conquer, divide and conquer. We'll elaborate more on that. Then I'll come to transforming a problem. Then we'll do problem solving exercises and resources. So For the problem solving today, I'll be doing more of just showing how to solve the problem. I won't really be doing a lot of like showing the code. I'll do more of explaining the concepts, because the code is out there for everybody to see. What's important is to understand the concepts. All right. You guys know me already, so I'll just skip this. What are we doing today? So we call our big picture diagram, where we kind of outline what happens when someone writes a program, saves it on their disk, and runs it on the CPU. So at the basic fundamental level, just going over this again, when you write your code in your Notepad editor, your editor, or whatever editor you use, and you save it on disk, that is stored on disk. When you try to execute the code, in that you double click it, or you run a script, or something triggers something, then that program is copied into RAM. And the CPU begins to read instructions to execute the program from RAM. So what this tells us is that all data structures during program execution are created and stored in memory. Yeah. And today we are going to be discussing sorting algorithms. And sorting algorithms are ways we can work on those data in RAM. So we've looked at data structures. All right. We saw arrays, and the key advantage of arrays were that the items are contiguously stored in memory. Then we looked at linked lists, which the items are not contiguously stored in memory, and they are linked through pointers. So arrays and linked lists are the fundamental data structures that you can have, and every other thing builds up from it. And when you're thinking of a data structure, you generally want to do three basic things. Some data structures have additional things, but we want to be able to insert items to the data structure. We want to be able to find items or search items. I want to be able to remove items. That is the whole point of having a data structure, right? We want to store data and want to retrieve data. So insert and remove is straightforward. And then if you want to remove it, or you want to remove it, you need to find it. So these are the three key operations that data structures have. And as for each data structure, I encourage you to like think about data structure and how these operations are. So going over arrays now. We know from arrays you can insert. If you want to insert into the arrays, right, you can insert to the back of the array in constant time. But if you are setting any other place, you have to shift all the items in the array forward. And to find items, last week we did searching, and the key thing to note when you're finding an item is that if the array is sorted, you can find an item in logging using binary search. But if it's unsorted, you have to do a linear scan, which is ORM. Now, I put some other columns there, like to find the kit item. So to find the kit item essentially means if you want to find your first item or the second item or the third item, whatever. So if it's sorted, right, you can easily find it in an array in constant time. You just go to that index. But if it's unsorted, right, you need to do a linear scan. And so remove is also like insert. So linked list, you can see the time complexities there. I won't really go over it since we've gone over it. I just included it here for completeness. We've gone over abstract data types. We know that different data structures have their advantages and their disadvantages, and it's important to know what you're trying to solve, how you want to represent it, and what is the most efficient way to solve the problem. So now, because I'm going to the algorithmic portion now, we're going to be using a combination of data structures going forward, just to see how we can solve problems. And the problems are not going to have an underlying theme, like maybe stacks or queues or things like that. It's just going to be having a problem, and then we see how we're going to solve the problem. Okay, so the deal of the day. So is everybody good with that introduction? Thumbs up if you are, or do you have any questions so far? Yes, okay. I'm assuming that was a mistake, but if you have a question, go for it. Okay. So sorting. Why do we sort? What are we trying to do when we sort? Why is it important? Now, the simple answer is to make finding items easy. Now, if you want to find items, it's easier to find items if you have an order than if you don't have an order. So it helps us able to find items easily. That's the main reason why we sort. And majority of the tasks the computer does is around finding items. It's around retrieving items, essentially. Because if you look at it, when you're running a program, it accesses memory continuously to be able to get data. And to access memory to get data, it needs to be able to find that item. So finding is very, very important. And that's why sorting algorithm is very important to understand. And it's also used to organize information in an easily accessible way. So for instance, let me give you an analogy. Let's say we have a dictionary of words, right? And the dictionary is not sorted. We just have a dictionary of words, and the words are in the dictionary anyhow. If the dictionary is not sorted, we want to find a word, we have to go from beginning to the end, right? That's problematic. But if the dictionary is sorted, you can be a bit more efficient. I mean, you look at, so what you just did is sorted, right? As a person, you just open a page. You look at the index. You look at what you're looking for. Look at where it starts. So let's say you're looking for A and you're on B. You definitely know you need to go back like that. So a variation of that, which is binary search, is what helps us find items easily when they are sorted. And that's important because without sorting the item or without organizing the item, we can't easily find it. And this is a very key point to note. Google searches, even Google searches uses some form of sorting because without being able to organize the information in an easily accessible way, they won't be able to give you your answer fast. So sorting is very, very important, and it's a key operation in computing systems. Okay, so let's move forward. So to be more precise, when we say we want to sort something, the input is a sequence of numbers. Now I use numbers here, it could be a sequence of anything. A sequence of numbers, and we want the output to be a permutation of that sequence of numbers in another form. But it's key to note that a sort of a particular collection is a permutation of that collection. And for those who are not familiar, permutation essentially means how you arrange states without order. So like if you have 1, 2, 3, and you arrange it as 3, 2, 1, and 2, 1, 3, they are permutations of the same structure. So the sorted solution is a permutation of the initial structure. It's just that in this case, the permutation satisfies some constraints, which means that every item must be less than or equal to the next item. If you are sorting in ascending order, if you're sorting in descending order, every item must be greater than or equal to the next item. So I pulled this out from Donald Kutz, is a famous computing guru, and the point he was trying to make here was that sorting is like most of what the computer does. Okay, so applications of sorting, where do we apply them? If you want to search for collections in the sorted, if you want to search for values in the sorted collection, we can easily find it to be sorted. We can easily remove duplicates and group items together. Even in databases, when you submit an item to database, when you store an item in database and you retrieve it, database is able to give you back your item quickly because it has a form of sorting that you use to store the item. When you create indices on databases to make you retrieve things faster, essentially what you are doing is you are sorting based on an index, and then when you want to retrieve based on that index, you do a binary search to that index and then retrieve what you want to retrieve. So it's everywhere, applicable everywhere in the world. Like if you want to match item in files, everywhere around us. So like look at the Gmail, for instance. The Gmail list is sorted according to certain order. Either it's sorted by the received time, or it's sorted by maybe the name, but there's always some form of sorting. And this is a general thing too, that whenever you have a UI and it's displaying a list of items, those items are usually sorted based on something. So we've seen that sorting is important, but from our perspective, why do we learn sorting? Because the truth is this: you will most likely not have to implement a sorting algorithm yourself in the real world. If you're implementing a sorting algorithm yourself, you are doing something wrong. Because there are people that have implemented those algorithms in the best way possible that can never conceive of. So from our own perspective, we study sorting algorithms because it gives us insights into algorithmic design strategies. So looking at sorting algorithm and knowing the fundamental idea behind it is what is more important to us. And we'll be learning the algorithms, definitely. But I want you to pay more attention to the ideas behind them as they carry over to other problems, which is the key thing you want to remember from this. The ideas carry over to other problems. after the session, I would go through a list of problems and we'll discuss some ideas on how to approach problems and all. And we'll also be looking at trade-offs and how to analyze algorithms. And this is because when you have an algorithm and you create an algorithm, you need to be able to analyze it to see if it's efficient or it's not efficient. So the key thing to note here is the sorting algorithm is important, but more important is to understand why the sorting algorithm works. What are the main ideas behind it? That is what is very important, not necessarily the code behind it. So because of that, I won't really be providing code. I'll be referencing visualizations, and I'll be linking to the code when necessary and explaining them. But I won't really be focusing on the code today. You can get the code anyway, once you understand the concepts. Okay, before we move forward, does anybody have any question on what we've discussed so far? Okay, we are still happy. Let's move on. Algorithmic design strategies. So when I was designing this, I was thinking of the best way to present this. And I thought it would be better to present the algorithmic design strategies and link them back to the sorting algorithms and just give you what the sorting algorithms are and how they work. So there are a couple of algorithmic design strategies that are generally applicable. We are going to be doing some next week, but the first one is brute force. Now, brute force is kind of the most basic strategy. It's essentially how you would design it if you were a novice in something. That's kind of the most straightforward way to do it. The very straightforward way to do it. And that's the first type of design strategy. We'll be talking about it more in detail. The second one is reducing the problem space. And this falls into two main categories, which is divide and conquer. Now, when you divide and conquer, you are reducing the problem space by dividing it into sub-problems. So the idea is you have a big problem, but you can't solve the big problem, or it's hard to solve the big problem. But you know you can solve a smaller problem. So you divide a problem into multiple problems. Could be 2, could be 3, could be 4. Doesn't matter. You divide it into multiple problems, solve each of those problems, then combine the results. That's divide and conquer. The other variation is, I came up with this, it's kind of multiply and conquer where, so in divide and conquer, right, you are reducing the problem space. There are two ways you can do it. You can either reduce the problem space or increase your solution space. The problem space is the problem you are trying to solve. The solution space is the solution to the problem. So you can either reduce the problem space or you can increase your solution space. I'll explain more as we go on. But that's essentially the opposite of divide and conquer anyway. And you also have decrease and conquer. And decrease and conquer is different from divide and conquer. In divide and conquer, you are dividing the problem into multiple problems. But in decrease and conquer, you are reducing the problem to one problem. So you're just reducing the problem space. You're not creating multiple sub-problems. You're creating one sub-problem. And the opposite of that is increase and conquer. So either you reduce the problem space or you increase the solution space. I'll explain as we go forward. Then the third strategy is to transform the problem. So if you look at the problem and you're like, okay, I can't solve this problem. What other problem related to this can I solve? So you can, it's just a way of thinking about the problem in a different way. And that gives us some insights into how we can solve the problem in different ways. Usually it entails, when you transform the problem like that, you have to take some trade-off. Either you take extra time or you take extra space. But sometimes the trade-offs are not too bad to make the algorithm not efficient. So we usually still apply it. And then that's essentially, so these are the 4 design, these are design strategies that we are going to be looking at today. And I'm going to be starting with brute force. Before I move forward, do we have any questions? Okay, so moving on to brute force. So for brute force, right, this is the simplest design strategy. And it's the straightforward way you will solve it based on the problem statement. So when you think of a problem, the first solution that comes to your head, or the first way to solve it that comes to your head, is usually the brute force. And it's not usually efficient, which is not, it's not bad if it's not efficient, because it's just a starting point. We use it as a starting point. And then it usually involves enumerating all possible solutions to a problem. And sometimes it's actually the only solution we have. Some problems are just like that, such that you have to enumerate every possible solution to the problem. Like if they ask you to generate all the permutations of the collection, there is no way than to just generate everything. There is no other better way you can do it. So it's important to note that brute force is not necessarily bad. It's usually as a stepping stone to solve the problem. And usually we start with brute force and then we try to optimize that approach going forward. So in the context of what we're trying to discuss, we want to sort numbers. So let's say we have a list of numbers and want to sort them. Assuming you gave this to a monkey, if you told the monkey if you arranged some things on the table that are ordered, and you told the monkey to order them, as long as it's not bananas, the idea is the monkey will start to arrange them in different ways because he doesn't know what he's doing. He's just trying to shuffle them. So just imagine you told the child to arrange something and the child doesn't know the order. The child is just going to be taking them and putting them in different places. So this is the basic kind of brute force. It's called monkey sort, bogo sort, or stupid sort. Essentially, what it means is you are generating all the possible permutations that you can have, and then you check if one is sorted. Then when one is sorted, we have our answer. So the algorithm is very simple. I check my list. Is it sorted? If it's not sorted, while it's not sorted, I just shuffle it. I just keep shuffling it. Shuffling it. So is this efficient? Open question. Do we think it's efficient? Thumbs up if you think it's efficient. Okay, good. It's not efficient, right? So the problem is it even correct? Let's start with, is the algorithm even correct? I'll go back to the previous. Is it correct? Let's start with, is the algorithm correct? Now, yeah, it's correct because we can find an answer, right? If we generate all the possible permutations and we are sure that we're going to generate all the possible permutations, we'll find the answer. But if you are just shuffling randomly, we might never get the answer. And we might be lucky that the first permutation we take is going to be the answer, right? That's the best case. But how likely is the best case? Not very likely, right? It's like probability of you winning a lottery. You could win a lottery, yes, but you are most likely not going to win a lottery. So that's something similar to this. So the problem with this is, it's just how is the important thing about it is the basic way you solve it. Just imagine you give this problem to a 5-year-old child and explain it to them in basic terms. That's the way they will most likely solve it. You just be shifting items around. Okay, so what's the time and space complexity of this? So we have best case, we have average case, and we have worst case. We talked about best case, average case, and worst case when we did our earlier sessions. So the best case, we find the answer in the first permutation. That's the best case, and we're good. But because we need to verify if the permutation is sorted, it's going to be O of n because we need to do a linear scan to check if each successive item is greater than the previous. It's greater than or equal to the previous. Now, for the average case, we have to generate all the permutations. And to generate all the permutations is n factorial. It's kind of a formula you should just if you are not familiar with it, just know it. That to generate the permutations is n factorial. There are ways to prove it, but we'll not go into that now. So to check if the permutation is sorted is n. So that gives us n factorial times n. That's the average case. But in the worst case, we might never find anything if we don't generate our permutations in an indeterministic way. If we just keep doing it randomly, we might never get anything. So it could be O of infinity. We could keep doing it forever. But if the permutations are not random, then it's going to be O of n factorial times n. And for the space complexity, the space of complexity is constant because we're not consuming extra space. So, is this correct? It appears to be correct because we'll find an answer. We will find an answer. If you keep running the algorithm forever, we will find an answer. Eventually, we'll find an answer sometime, but it depends. It might take too long. So the key thing to note with correctness is not enough. The fact that an algorithm is correct doesn't mean that algorithm is good. Because if it's correct and it takes us 1 million years to get the answer, the algorithm is of no use to us, right? So that's why efficiency comes in. Now, to put this into some context, into how bad this is, our machines generally, CPUs, they run operations per second. And a modern CPU can run about 10 to the power of 8 operations per second. Now, when you write your program and you store your program in memory, it's usually compiled or interpreted to some form of assembly instructions, either by the compiler or the interpreter, somehow. But at the basic CPU level, it's going to be executing some instructions. So your program is compiled to a certain number of instructions. And if you want to get how long your program will execute, You take the number of instructions your program is going to run and divide it by the number of operations per second of that CPU. And that tells you how long it's going to run. So let's assume you could generate and test one permutation in an operation. We need 800 years for an array of size 20. That's how bad the algorithm is. For an array of size 100, that would take like 10 to the 142 years. So we can see that it's not efficient. It's correct, but it's not efficient. And this is a key thing to understand here. The algorithms that are correct and are not efficient. And with from a real-world perspective, you're looking for algorithms that are efficient within the context of what you're doing. So sometimes you may not really go for the most efficient algorithm because it's hard to implement, but you need sufficient efficiency for the problem you're trying to solve. Okay, so are we okay with monkey sorts? Any questions? Perfect. Now, let's continue to a better sorting algorithm using brute force and enter selection sorts. Now, what does selection sort do? So if we think about it, right, we want to sort the items in the array. If we take the smallest item and put it in the first position, that part is sorted. If we take the next smallest item, put it in the second position, take the next smallest item and put it in the third position. If you continue doing that successively, you will sort the array. And that is the brute force way of solving it. So there are two ways you can do it. You can either locate the smallest item and put it in the first place, and so on, or you locate the largest item and put it in the last place, and so on. So because it's sorted by repeated selection, it's sorting by repeated selection. That's why it's called selection sort. So I'm going to be going through demos. Let's start with the first demo. Okay. Is this legible enough for everybody? Actually, I think this is better. Is this legible enough for everybody? Thumbs up if it's legible. Okay, cool. So now for selection sorts, right? I'm going to create a smaller array. I want the arrays to be small so that I mean it's easy to you have a question, go for it. Okay, I think that's a mistake. So we have an array and we want to sort it with selection sorts. What do we do? The first thing is we find the smallest item, right? So we do a scan. 10 is currently the smallest for this iteration. We find the smallest item, which is 10, right? And put this in the first position. Now, one key thing to notice, 10 is already sorted. 10 is in a sorted position of the array. So it's dividing the array into a sorted position and an unsorted position. So 10 is in the sorted position. So what do we do now? If we have this portion has been sorted and this portion is not sorted, if we repeat the process and we take the next smallest item and put it in the second place, then we have our solution, right? So that's what we're going to do. We start scanning for the next smallest item. We see that the smallest item is 14. We put this in the second position. Now the first and second part is sorted. The last three are not sorted. Are we getting the idea? We repeat the process again and find the next smallest item, right? And put it in the third position. I'll repeat the process till we get to the last item. And we are sorted. So this is essentially how selection sort works. You select an item and put it in the right position. Now you could do it the other way where you select the maximum and put it in the last position, which is what I'm going to be showing here. Yeah. So run. Okay. So in this case, this is another application of selection sort. But in this case, we are looking for the maximum, right? 978 is the maximum. Now we take it to the end. It's the same thing as the previous one. It's just that we are doing it from the other side. The next maximum now is meant to, from looking at it, we know it's 845. So we scan through, find the next maximum, and put it in the next position. Find the next maximum, which is 717 now. Put this in the third position, in the third to the last position, sorry. The next biggest item is 523. So we scan, but it's already in the position, right? So we just put it in that position. And when we do it for all the rest till we are done. I'm just gonna click through. That's essentially how selection sort works. And we are sorted. Okay. So for the code, I found this sorting visualizer that gives you very good. The reason why I included this is because it has the code for all the 5 languages. I was thinking of providing the code, but then I was only going to provide for Python. But this sorting visualizer, we have the code for like all the 5 languages. So you can pick whichever one you are more familiar with. But I'll go with Python to explain. Okay. So essentially what they are doing here is just going through the array, and at each iteration, they are finding the minimum index. So they start from the beginning, find the minimum index, and then they swap the minimum index with that position continuously. So that's essentially what selection sort does. And so let's analyze it. What's the time and space complexity? Right. So if we look at it, how do we analyze this? If you go back to our first class, right, when we have double for loops, right, and we are kind of like iterating twice, we know that it's quadratic somehow already. We know that that's going to be quadratic, which is n squared. But if we want to be more rigorous, the first time we are looking for the minimum element, we have to scan through the entire array, which is n. When we put the minimum element in the right position, right, we have to scan through n minus 1 element left. When we put the second minimum element in the right position, we have to scan through the n minus 2 elements that are left, continuously till we get to the last element. So this is the summation for the work done in the inner loop, which essentially is O(n) squared from our previous interactions, our previous lessons. And the space complexity is constant because I'm not using extra space. Is this correct? Yes, it appears to be correct because it will find an answer. Is it efficient? O(n) squared is not too bad. We can use it in some scenarios, but you can do better. So before we move forward, do you have any questions on this? On selection sorts? Okay. So the key idea to note here is that it's brute force. We are just doing it the basic way we'll solve the problem without using any complicated algorithmic strategies. Okay, now we move on to bubble sort. Now, bubble sort is a variation of the brute force. So if you look at selection sort, at each iteration, we're putting the smallest element in the correct place. So essentially, we are trying to find the smallest element each time. Now, bubble sort does the same thing, but it does it differently. Instead of finding the smallest element, right, it bubbles up the smallest element or bubbles down the maximum element. However you want to look at it. The visualization is the best way to understand this. So I'll go forward. The visualization. So now we have this array that we want to sort. How do we sort it? We need to put, so essentially we need to either put the largest element to the right after this iteration, or we need to put the minimum element to the left after this iteration. But in this case, you're going to be starting left to right. You could do it either ways, it doesn't matter. So for each element, to compare each successive element, 792 is greater than 326, all right? So we swap it. We move forward, we compare 792 and 822. 822 is greater, we don't swap, we just continue. right? 822 and 223 is bigger, we swap. So essentially, we compare the items successively in pairs and swap the biggest and swap the biggest to the right position. Or if the biggest is already at the right position, we leave it as is and continue. So we see now, we compare 822 and 253. 822 is bigger than 253, right? So we swap it. 822 and 955. 955 is bigger, so we don't swap. 955 and 269. 955 is bigger, we swap. 955 and 159. 955 is bigger, so we swap. So what you need to understand is, after this iteration, the biggest item is at the end. That is the key thing to note. So if you can assume that this part of the array does no longer exist and repeat the same process on the left-hand side, you will get the next biggest. And if we repeat that process continuously, we'll sort the array. So we start the process again. We start from beginning. Compare. 792 is bigger, so we leave it. 792 is greater, we swap. 792 is greater, we swap. 792 is not greater, so we leave it. 822 is greater, we swap. 822 is greater, we swap. Now, the second largest item is there. So you could visualize it and think about it in such a way that once you put an item in sorted position, you are not considering that item again. So this 822 now will never be considered again. 955 will never be considered again because this portion of the array is sorted. And that's what key thing to note with solving problems. Like, you can see that they are trying to build the solution incrementally. Right? They are building the solution incrementally little by little. But each successive step brings us closer to a solution. And one thing to also notice is that you discover that the array that we are scanning to find the next largest element gets reduced little by little. The first time it's reduced by one, second time it's reduced by one again. So it keeps reducing. So that is essentially what we call reducing the problem space. We can see that the right is increasing. And that is the solution space. So that's what we call increasing the solution space. So in this case, we are reducing the problem space as we go on, and we are increasing the solution space. So let's see the next one. Next iteration. So we start at the beginning. We swap since 3 to 6 is bigger. The same process till we get this to the right position. You see the pattern. If the solution space increased, the problem space reduced. And that's one key thing you should try and note when you're trying to solve problems. How can I reduce this problem to something I can solve? Either by chipping away at the problem or by dividing the problem. Now, we continue. So we expect 3 to 6 to be in that position now. Then we expect 269, and essentially the rest is trivial from here. And we're done. So that is essentially how bubble sort works. It kind of does the same thing as selection sort, but it does it in a different way. And it's less efficient because it keeps swapping. It does too much swapping. So for the code of bubble sorts, I think we have it here. Oh, sorry, this website makes noise. So essentially what they are doing is they are looping through the array up to but not including the last element, because they are going to be they are going to be comparing with the next element. So if you are the second to the last, you don't want to, if you are the last, you don't want to compare it to an element that exceeds the array. Your last comparison will be the second to the last element and the last element. That's why you have this n-1 here. Now, what they do is they iterate through that range, right? As the range that we are considering. And then if this item is greater than the next item, then they swap. This is how you swap in Python. You can swap it in one line. I think in C or C++, in Java, you have to do this. Yeah, you have to use a temporary variable. I don't know, C++, okay, you have to use a function and use pointers. But in Python, you can just swap directly. So this is essentially how bubble sort works. Questions before we move on? Okay, we are still happy. What's the time complexity of bubble sorts? Now, in bubble sort, the best case for bubble sort is O of n. And why is it O of n? Let's see. If the array is sorted, we check. We don't do any swap. Notice we are not doing any swaps. Now, the reason why it's O of n is because you can check if you did a swap. If you didn't do any swap, then you know you are done. So a sorted array with bubble sorts that is efficiently implemented will give you O of n if it's sorted. If you're trying to sort a sorted array. Notice that with selection sorts, it's not the case. Because we don't know, like with selection sorts, we don't know whether the items to the right are bigger or not. So with selection sorts, right, you notice that with selection sorts, we have to scan everything to find the minimum item and put it in the right position. Now, at this point, we don't know anything about this other item. So we still have to check again for the next minimum. So this doesn't apply to selection sort. But bubble sort, you can have a best case of O of n. But is it really useful to us? Not really. I'm just including it here just for like explanatory purposes. For the average and worst case, similar to selection sort, right? What's the total amount of work we do in the inner loop? For the first time we go through the inner loop, we do n work. The second time we do n minus 1 work. Because the reason why we do n minus 1 here is because we've reduced the problem space. We reduce the problem space 1 more, becomes n minus 2. N minus 3 till we get to a single element that we can solve. And if you sum up this is n squared. So space complexity is constant because we're not really doing anything. Space complexity is constant. So is it correct? It's correct. Is it efficient? Not too bad, but we can do better. Okay, so any questions on brute force before we move forward? Okay. So we're done with brute force. Now we've seen that brute force gives us the solution, but brute force is not the most efficient we can get. So we want to find ways that we can come up with more efficient algorithms. So move into decrease or increase and conquer. Now, how does this work? There are two ways you can do it. Like I said, you can either decrease the problem size or you increase the solution size. So if you decrease the problem size, you decrease the problem from size n to size n minus 1. Now, you assume that you solved n minus 1, right? And then you solve a problem of size n using the solution of the previous. Now, there are two ways you can do it. You could do top down or you could do bottom up. I'll explain with an analogy later. And if you want to use recursion for this, it results in linear recursion. Linear recursion in that we make a recursive call each time. So we are creating one subproblem. Or you could increase the solution space and do it bottom up. So you assume you have a solution to a problem of size n. And then you include n plus 1 in the solution. You include the next element into the solution using the previous solution you have. So essentially, what you are trying to do here, you are trying to chip away at the problem. You have a big problem that is difficult to solve. So you are trying to reduce the problem to see if you can solve the simpler version of the problem. With decrease and conquer, you are reducing it linearly, like you are reducing it 1 by 1, or 2 by 2, or 3 by 3, doesn't matter. Now, let me give an analogy. So let's say we have people on the line, right? And we need to count the number of people on this line. Let's say I'm the manager and I need to know everybody that is on this line. Now, for me, it's so much work if I want to count them because I need to start counting them 1 by 1. But there are two ways I could do it. I could ask the last person on the line, how many people are ahead of you? Last person doesn't know, right? last person can say, okay, well, I know I'm one person, but I could ask the next person how many people are ahead of them. Now, that next person is kind of like, I'm one person. I don't know how many people are ahead of me, but I could ask the next person. Now, if they keep asking each other that question, and they get to the person in front of the queue, the person in front of the queue be like, nobody's ahead of me, and I'm one person, right? So the person in front of the queue tells the other person, there's one person ahead of me. Or the second to the last person can say there's one person ahead of me. Or the person at the front of the queue can say I'm one person. However you look at it. Now the second person knows that there's one person ahead of him. And if he adds himself to that, that becomes two people. And he can tell the third person now that, okay, or she can tell the third person that, hey, there are two people ahead of me and I'm one person. That's three. Sorry, there's one person ahead of me and I'm one person. That's two. The third person does that. There are two people ahead of me and I'm one person. That's three. And keeps returning the answer back. See, they get to the person at the back of the queue. Now, notice the sequence of how this went. We start from the back of the queue and we ask the question going to the front. Now, note that when the first person in the queue got the question, the last person at the queue is still waiting for an answer. And that is top down. You are going top down. So the top asks the question and gets to the bottom, and then the answer is returned back up. That's essentially top down. Now for bottom up, there's one way I could do it. The person at the back of the queue can say, you know what? I'm one person. And tell the next person in front of her, I'm one person. Add it to yourself. So essentially, that's basically you do where you take numbers, right? 1, 2, 3, 4, and you start doing numbers. Now that's bottom up. But you can see that we could solve it in that way. Either we go from back to the front or front to the back. The key thing to understand with going top down is that you can't get your answer immediately because the person that has the question is still waiting for an answer. And that's where recursion comes into play. Essentially, the person at the back of the queue asks the next person recursively, how many people are ahead of you? That person asks recursively, how many people are ahead of you? How many people are ahead of you? And then the answer gets returned back up. So that is the idea behind decrease and conquer. You chip at the problem. You have a big problem. You can't solve it. You begin to chip at the problem little by little till you can solve it. Okay. So essentially, that is what it is. That's what this is. No, so how can we do this now? And here comes insertion sort. We can reduce the problem space by 1 each time. Like I said, if we want to do top down. So we just assume that n-1 elements are sorted and we add the nth element. Right? Or we could do bottom-up iterative. For the sake of time, I'm just going to go through the bottom-up iterative. We're still going to talk about recursion later, so I won't really delve too much into recursion. I just wanted us to know that strategy going forward so that we can watch out for it and be able to apply it. So how does insertion sort work? Demo time. Okay, so now I want to use insertion sort to sort this. Now, this is the entire problem space. So insertion sort, essentially, doing bottom-up is kind of like, okay, the first item says, you know what? I'm the only item, right, in the solution space. So your solution space now is just the first item. And since it's the only item, is sorted because it's the only item. And if you have only one item, that item is sorted in that collection. You can think of it that way. And you can also think of this as the base case as well. We'll talk more about that in recursion. So now, since this is sorted, we've increased our problem space and we've increased our solution space and we've reduced our problem space by 1. Now, for the remaining part of the problem, right, we want to increase the solution space by 1, right? So the thing is, to be honest, we can take anybody out of this collection and add them to the solution space. Like, you can literally take anyone and try to add it to the solution space and you still get your answer. But because of the efficiency of that is bad, you take the next item, the first item in the problem space, because it's just easier for you to pick that. Since the array is the solution space is going to grow anyway. But the point I'm trying to make is you can just think of it as you picking randomly and trying to solve. In fact, that algorithm is it's an algorithm that I don't know what the name is, but that's the kind of insertion decrease and conquer algorithm. But again, insertion sort is a variation of this. But I want you to get the idea behind it and why it works. So now we want to increase our solution space. Now to increase our solution space, we try to insert it in the sorted order. We take away from one problem and try to insert it in the sorted order here. Now, because this is greater than this, we don't need to do anything. Now, you can see what happened here. This problem space is solved. When we wanted to increase, this solution space is solved, sorry. When we wanted to take the next item, all right? When we wanted to take the next item, we saw that we have to insert this item in the sorted position on the left, which means we have to shift the item. Now the solution space has increased. The problem space has reduced. For the next item now, we have to shift it and insert it into the right position in the solution space. We've checked one, we solved that. For this one now, because it's the smallest, looking at it visually, we know that we're going to have to swap it all to the end, all to the first element, and which is exactly what's going to happen. Solution space has increased, problem space has reduced. We are chipping away at the problem. We are decreasing and conquering. Now, for this one, because it's the largest, right? We don't need to do any swaps. We are happy. We just let it go. We don't need to do any swaps here. Then for the next item, we need to swap it into the right position. For this one, we have to take it right to the back now. There we go. And then we have it sorted. So this is essentially insertion sort. In this case, we started with one problem in the one solution, one element in the solution space, reduce the problem space, and we kept going that way. So we got to the end. Okay. So for the code of insertion sorts, excuse me. Essentially, what we're doing is we are looking through the array, right? And for each of so this here, we are looking through the array to increase the problem space, to increase the solution space. And for each of the problem space left, we are checking and we are trying to insert it into the solution space. Now you can go more into this later just to like kind of get it, but I don't really want to delve into the code now because the code is easily accessible. I want you to mainly understand how it works so that when you're reading the code, it's easier to follow. So that's insertion sorts, essentially. Now there's a top-down version of that. I won't deal with that. We did bottom-up now. There's a top-down version of it, but I won't deal with that. We'll do that when we get to regression. Now, what's the time and space complexity? For insertion sorts, the best case is if it's a sorted array. If it's a sorted array, then what happens? Let's see what happens if it's a sorted array. Say it's a sorted array. Notice that we don't need to do any swaps. This is in the solution space. When we increase it, it's in the right position. The right position, the right position, the right position. So that's why it's open for the best case. And you might think that insertion sort, because the worst case of insertion sort is quadratic. Because it's similar to what selection sort and bubble sort are doing. It's just that it's a bit more efficient about it. The average and the worst case is n squared because you have n-1 recursive calls. Sorry, let me use the bottom up. That was using the top down. So the sum of the work done in the inner loop is n-1 plus n-2 plus n-3 plus 1. Do you have any questions on the time and space complexity of insertion sorts? Are we still alive? Mhm. Okay, because I just want to make sure that like folks are understanding what I'm presenting. Okay. Okay. So for top down, we'll talk about it next week. I will come back to this next week. So correctness and efficiency, is it correct? It's correct. Is it efficient? It's decent, but we can do better. But one thing you need to note about insertion sort is efficient for small inputs. And in fact, there's a variation of a certain algorithm called team sort that Python uses that combines insertion sort and merge sort. But insertion sort is efficient in some cases. So if you think about it, let's say you have items that are almost sorted, right? And you want to sort those items. Insertion sort is very efficient. Or, excuse me. Or let's say, or the other thing is, let's say we have, so let me see. So let's say we have items that are coming in a streaming way, in that we don't have all the inputs initially. We are getting the inputs one by one. Insertion sort is very efficient because we are essentially inserting an item into the right position. Okay, so now we've seen decrease and conquer. Decrease and conquer or increase and conquer, it reduces the problem space by one and creates a new problem. Now, but in divide and conquer, we divide the problem space into multiple problems. So instead of creating one sub-problem, we create like multiple sub-problems. But do you have any questions on decrease and conquer before we go to divide and conquer? Because it's going to get very interesting from here going forward. Okay. So for divide and conquer, we are dividing the problem into several smaller instances of the same problem. Most often it's two. It could be more. And then what we'll do is that since we have the problem that we reduce into smaller problems, we try to solve the smaller instances using recursion, typically using recursion. And then once we have the solution to the smaller instances, we combine the solutions back to the bigger problem. So this results in tree recursion because at each time you are recursing to multiple branches. So this creates like a tree recursive structure. And this is kind of the most complicated kind of recursion you can have, a tree recursive structure. So in decrease and conquer, we're creating one smaller problem, which created another smaller problem. And that resulted in a linear recursive structure. In divide and conquer, we are creating multiple smaller problems, which creates multiple smaller problems, and so on. And that results in a tree recursive structure. So we'll talk about this in recursion. But essentially, the idea of divide and conquer is I have a big problem. I can't solve it. It's too much work. And I'm lazy. But I can break it down into smaller problems. And those smaller problems can be broken down into yet smaller problems until we have the problem so small that we can solve it. So let me use this analogy first. So let's say I need 1 million naira, right? 1 million naira is too much. I don't have 1 million naira. It's too much money. But if I go and ask somebody to give me 1 million naira, it's too much work for them, right? What can I do? Let's say I have 10 friends. If I ask 10 friends to give me 100,000 naira, I think it's more likely I'll get that than asking one person to give me 1 million naira, right? So I could ask my 10 friends, give me 100,000 naira, please. I'll give you back whatever. Now, each of those 10 friends, maybe they don't have 100,000 naira, but then they're like, okay, I know someone that can give me 10,000 naira. I know 10 people that can give me 10,000 naira. And they go ask those 10 people to give them 10,000 naira. Each of the person looking for 10,000 naira, maybe they don't have it, but they know 10 people that could give them 1,000 naira. Each of the person looking for 1,000 naira, maybe they don't have it, but they know 10 people that could give them 100 naira. You agree with me that it's much easier to go ask for 100 naira than to ask them for the initial problem, which was 1 million. Now, if you get to combine all those, all the money you've gotten and start combining it back up, you get your big, you solve the problem. So that's one way you can easily get money. If you can get 10 people to give you something, maybe you can get money. The problem is getting the 10 people. But you get the idea. That's exactly what divide and conquer does. Takes a big problem, breaks it down into smaller sub-problems, and try to solve it. Now, in my first example, I found 10 people that could give me 100,000 naira, right? But maybe I have a rich friend that can give me 900. And I ask somebody else to give me 100,000. Now, it doesn't matter whether I divide this into 10 problems, or 2 problems, or 3 problems. The most important thing is that you're dividing the problem for divide and conquer. Okay. Now, back to this analogy here. Counting people on a line. If you want to divide and conquer here, what do we need to do? It's kind of hard in this case, right? But what we could do is we could kind of divide the group into half and assign managers to them. Then divide those groups into halves again, assign managers. And then ask all those managers to count the people beneath them. But you need to understand the key thing here. You need access to the entire collection. Notice that we decrease and conquer. The person at the back doesn't know how many people are in the front and doesn't care, right? He just does it. But with divide and conquer, you need access to the entire problem space. So this is a key decision to make, because when you have some algorithms are streaming algorithms. Like, let's say I don't have all my inputs and I'm receiving my input from an API periodically, and I want to sort them in memory so that I can access them later. A divide and conquer algorithm cannot work. In that case, I need to use a decrease and conquer algorithm that can insert it into a sorted structure. Because each time I insert it into a sorted structure, that's going to be O of n if I use insertion sort. But if I use a divide and conquer algorithm, it's going to be more expensive. So you can see that even though insertion sort looks like it's not efficient, it has its use cases. It has where it's very applicable. And this is a key thing to note with all these algorithms. Like, the reason why we study all of them is because some of them look very inefficient, but there are cases where they shine. Each algorithm has its upsides and downsides. Some have more than others, and some are more useful than others. But they all have their use cases. The only one I know that doesn't really have a good use case is Bootcamp sort. That's just for educational purposes. Okay, so now, are we okay with divide and conquer? Do you understand divide and conquer? I think we are going to be doing more divide and conquer next week. So yeah, we're going to be more divide and conquer next week. Yeah. Okay. Any questions so far? We're very quiet today. What's happening? Are we tired? Is the lecture not interesting enough? Or is the topic a bit funny? Okay. So, merge sorts, the first type of divide and conquer algorithm. What we do in merge sort is we divide the array into 2 subarrays based on it. I think we are still new to the concept. Okay, that's fine. I understand. It's to be honest, algorithms are a bit difficult, especially if you are new to the concept. Data structures are a lot more easier than algorithms, and it takes some time to really get to understand them. So with merge sorts, so every divide and conquer algorithm follows these 3 strategies. You divide the problem, you solve the smaller problems, and you combine your results. Now, different algorithms do it in different ways. So what does merge sort do? It divides the array into 2 subarrays based on their indexes. It solves the problem on the smaller arrays by recursively sorting them. Now, one key thing to notice that in my analogy of me asking 10 people to give me 100,000, I don't really care about how they solved it. I don't care about how they got the 10,000, the 100,000. I just know that I'll give me 100,000 and I'm collecting everything together. So that is one key thing to know. So when you are trying to understand how to deal with recursion, think of one problem at a time and think that you have the solution to the sub-problems. So if I have a problem and I have a solution to the sub-problems, I don't know how they got that problem. I don't know how they solve the problem. Can I get a solution for myself? If I can, then I can solve the problem recursively. And that is a key thing to note in recursive algorithm generally, in recursion generally. So we make sorts. What do? We divide the array into subarrays. Now, those subarrays get sorted. How they get sorted, we don't know. And we honestly don't care. But then when they are sorted now, we need to combine them. So the question I will use to, if I have two sorted arrays, can I combine them to give me one sorted array that encompasses the two of them? That's the fundamental work in merge sorts. If you understand that, you've understood merge sorts. Given two arrays, can I merge them in a sorted way? Each of those arrays are sorted. But then I want to create a bigger array containing the two of them that is sorted. If I can solve that problem, then I'm done. I can solve merge sorts. And that is the key thing it does in combining. So combine the two sorted arrays by merging them together. This takes some work and extra space. So let's quickly look at a demo. I think a demo will make it clearer here. So with merge sorts, let's run. So now I want to sort this array. It's too big. What do? We break it down into smaller arrays. Now you agree with me that sorting an array of 4 items is easier than sorting an array of 8 items. Right? Good. So now I'll talk more about this in recursion. But when you have a tree recursive structure, or when you are doing recursion multiple times, you can only follow one path at a time and backtrack to the other paths. So now we follow the one on the left. We could have followed the one on the right, so depending, but we'll follow the one on the left. Now that splits it into two smaller problems. You agree with me that it's easier to sort an array of 2 elements than an array of 1 element. But we are still lazy. Sorting an array of 2 elements is too much work, right? We split it out again. Now, an array of 1 element is sorted. We know that, right? Like, if you are the only one in the element, you are sorted. So, 310 and 639 are in sorted arrays. Now, the question now becomes, when I go back to the parents, can I combine the two of them to give me a sorted array? Well, it's easy, right? Since there are 2 items. If the left is smaller than the right, put the left before the right. If the right is smaller than the left, put the right before the left. Essentially, that's what we have here. Now, in this case, because they were already that way, it's not going to show. But as we go forward, we begin to see the differences. So now, during this process, now there's a backtracking that occurs back to that parent. Now, this array is sorted, and it goes back to its parent that says, you know what, I'm done. Now, we'll now go to the right of that to see the solution. The left is sorted, but the parent wants to now do the right. Backtrack to the parent, and the parent goes to the right side. Now we split this into 2 items. It's easy to sort an array of 2 items, right? Okay, we are able to sort it and combine the result back. Now, when we get to our parents, the parent is now like, okay, I have 2 sorted arrays. I have 2 arrays that are sorted. How can I merge them to give me a sorted array that contains the 2 elements? That is the fundamental problem to solve a merge sort. Now, the way you do that is you have 2 pointers to each of the arrays. Since the arrays are sorted, right, you know that the smallest is going to be at the beginning of the arrays, right? So if you take the smallest from one of the arrays, right, that's the smallest, then the next item there could be the next smallest. So essentially, you have 2 pointers, and then when you take an item from an array, you move the pointer forward. And if you continue doing that till you get to the end, you will get a sorted array, essentially. That's what we are doing here. So it has a pointer and says, okay, since the left is sorted and the right is sorted, which is the smaller one? 310 is small, 295 is smaller, right? So it puts that there. Take the 2 smallest and the 2 largest and we sort. So you can just take the two smallest, I think. I don't think you need to take the two largest. If you take the two smallest and put them in place, you get your answer. Or I'm not sure what you are trying to drive at. Maybe I'm missing your comment. Okay. So for this one now, we move the pointer forward to the next item, right? But the 310 is less than that. So we take the item from this array and then we move forward and compare the next two items. Like that, like that. Now we've gotten an array of 4 elements. That was easy, right? Now we go report to our parents that we are done. The parent now goes to the right to do the right child. Essentially. So this is why I call it tree recursion. Because if you visualize this like a tree, and each tree has children. So you get to the base where it's trivial to solve. And then they begin to return back to their parents. So if you can visualize every recursion you do as a tree, then and you really understand it, most of your work in understanding recursion is done. So now we repeat the same process here. We split it into two smaller problems. Split it into smaller problems. Same process, merge. We're good. Go back to the parents, split into smaller problems. We essentially do the same process we did on the left to get a sorted array here on the right. Boom. Now we go back to the parent. The question now becomes, how do we merge these two arrays? So like I said, you're going to have two pointers, a pointer on the left and a pointer on the right. So the pointer is going to start from the first element. So we are comparing the first two elements. Which one is smaller? We put the smaller one, and then we shift the pointer. Because the smallest is gone. So the next smallest is the next one, right? Then we compare that with the smallest on the other side. Now you can do this because the array is sorted. So you are sure that this item here is smaller than everything on the right. And this item is smaller than everything on the right. So the smallest between this item and this item is the smallest you can get. We repeat the process. Find the smallest. The smallest is 310. We put it there. We increment the pointer to the next one on this side. We compare them. Which one is smaller? 317. We increment the pointer. Which one is smaller? 488. We increment the pointer. Which one is smaller here? 511. We increment the pointer. Which one is smaller? This. Which one is smaller? This. Now, we get to a point where one of the arrays will finish before the other. One has to finish before the other, even if they are equal. At that point, you can just add everything in the final array. So in the code, that's actually how I implemented it, and then you're done sorting. You need to note, divide the problem into multiple sub-arrays, solve each one, and then combine the results. And that's merge sort. So back to the code now. So for merge sort, in fact, I'm gonna try and see if I can find something that makes it trivial. Perfect. So look at this code here. The algorithm is very simple, right? While left is less than right. So in short, while we have greater than one element in this array, while we have at least one element in this array. Sorry, left less than, while we have at least two elements in this array. If we have one element, we are done. For left to be greater than right, we have to have at least two elements in the array. So while we have at least two elements in the array, we find the middle, we merge sort the left, we are splitting it by the middle. We merge sort the right. Notice that this merge sort, they are recursive calls, so we don't need to do anything here. But then we now merge the two of them. So the major work is in this merge position here. So what do we do in merge? Essentially what I explained. Essentially we create a new array because we need to take extra space to create an array. And then we loop through the first one. So essentially what we are doing here is that we are creating we are creating a new array here. This L array is like we are creating a new array here. Then we loop through each of the two arrays. If the left is less than or equal to the right, we choose the left and increment it. If not, we choose the right and increment it. Then when we are done, we just add whatever is left. So usually when we are done, one array will have elements left, one will not. So if you add the two, it doesn't matter if you are adding an empty array, it's fine. So they are adding those elements to the sorted part. That's actually what they are doing here. And that is merge sort. Any questions? Okay. So what happens? If you visualize everything, like I said, this is what essentially what happens. There's recursion. And then it's merged here. So what's the time and space complexity of the merge sort? Now this is our first time we are going to analyze the recursive structure. So I might take some time on it. What's time and space complexity? So generally, if you want to think about the entire work we do, this is essentially what happens. We go down, splitting down, and then we merge back up. So what's the work we do? You can visualize your recursive structure like this. And you can determine that if this is the entire recursion I did, the total amount of work done in this recursion, in this operation, is the sum of all this, everything here. So the question is, what is the amount of work I'm doing in each circle here? That's the fundamental problem I'm trying to solve. Now, in the case of merge sort, it's not easy to find. It's not easy to know the amount of work we are doing in each circle, because this is a part of the sub-problem. But essentially, when we are merging takes linear time. So within each recursive call, we are merging. So let's say we are at this, let's say the third position now, right? Let's say we are at the third position, right? In this particular circle here, we are doing n over 4 work to do the merging. And if we add up that across this line, we discover that we do O of n work on this line. And if we look at the work we are doing in the upper place too, we are doing n over 2 work plus n over 2 work, which is the O of n. So we are doing O of n work across all levels. The question now is, how many levels do I have? Right? How many levels do I have? I'm going to have log n levels because I'm dividing it by 2 each time. That's how we arrive at n log n. That's the intuitive way to understand it. There are more complicated mathematical ways to derive it, but I don't think that's really important. But I'll talk more about this in recursion next week when we talk about recursion in depth. So essentially, the key thing to know is you have log n levels of recursive calls because it's a balanced tree. If you look here, it's a balanced tree. So we have 8 items, right? And we have 4 levels, which is log n plus 1, but the plus 1 is irrelevant because log of 8 to base 2 is 3. So that is how we come at n log n. Log n levels of recursive calls, and each work done at each level is O of n. Now, in this case, the reason why we took that approach is because it's not trivial to know what happens in each circle. It's easier to look at it from what happens across every line of the recursive structure. So that's the approach we took. In some cases, you want to know what happens at every circle, but we'll talk more about that in recursion. So that's how we get n log n. For the space complexity, merging takes extra space, which is O of n. And then the recursive call stack takes log of n. Because the recursive call stack, right, it grows on a particular path each time. So it's going to go like this, if you can see my mouse. And this is the maximum it will go. I'm back here, like this, back up. But the maximum to go is the height, which is equivalent to the log of number of items because we are dividing each item by 2 successively. We are dividing the problem into 2 sub-problems, evenly. Now, the reason why it's log of n is because we are dividing the halves equally. If we were creating two subproblems and we were reducing it by 1 each time, we'll have a skewed tree, which will become O of n. So that's why it's important to divide the problem evenly. Because if you don't divide the problem evenly and you reduce one, so let's say you can say, okay, maybe I'm removing 3, and then I recurse to 3 and I recurse to this left. Essentially, we have reduced it to insertion sorts. If that makes sense. So the key thing in divide and conquer is you are dividing the problem to multiple subproblems. You are not just reducing it. If you reduce it, then it's not divide and conquer, it's decrease and conquer. Okay. So that's it for merge sorts. I know this is a bit involved. Any questions on merge sorts? Okay, go for it.
All right, so I kind of have a question, right? So the question is, for the merge sort, right? I know the fact that we are actually breaking it like into two, then using L and R approach, like left and right, right, and going up again. So now the thing is, in the what's it called, in because it takes more space, extra space, right? Because you're breaking something into two, and you have to like run simultaneously, right?
Yes.
So now the question I'm having is there a possibility where you can break it into more than two?
Yes, you can.
Like instead of like it's going to take extra space. I know, way more extra space, but it's going to be faster. So I don't know if there's something like that. So that's the question.
That's actually a very good question. So yes, the answer to your question is yes. You can break it into more than two. You can actually, like, that is one way you could do it. You can break it into more than two. And in that case, you are creating multiple subproblems. So the efficiency is, let me see. You essentially are going to have n log n, but it's going to be log to base of 3. So it's n log to base 2 of n better than log to the base of 3 of n. That will determine if it's more efficient or not. I don't know the answer to that question. But you are still going to have an n log n efficiency structure. And yes, you can do that. It's very possible. And in that case, you are going to have a recursive structure where each parent has 3 children. That's what you have. Does that answer your question?
Yeah, so that brings me to like the second question, because I wanted to find out if it's possible first before I ask the second question. The second question is now, what if you now have like, okay, you break it into like, let's say 3, you break it into 3, and you find out that one the data set or the list is a result, let's say an even list, right? So meaning that there's going to be one that will be like at the extreme or maybe somewhere, right, after breaking it. So if you want to break it to 3 and you find out that, okay, this thing can be broken into 3 because it's not evenly distributed, so what happens then? Is there like an exceptions to, okay, let me be honest, let's say you have n log n, right? Is there a subset of n log n where you can okay, because this is not fitting in this this break chain, we could go lower in the n?
Okay.
Do you understand what I mean?
Yeah. So good question. So back to that brings to the question of you having to define what your base case is. Now, the base case is what will determine when to stop the recursion. So if you are grouping it by 3 items, right? And let's say you determine that, okay, your base case is an array of size 3. And then if you have an array of size 3, you break it into 1, 1, 1, right? And then you're done. So in that case, you could do it that way. and ensure that you don't have greater than, let me see, you don't have greater than 3 elements to be able to recurse. You don't have less than 3 elements to be able to do another recursion. That's one way you could do it. And that doesn't really affect the time and the space complexity. But I'll need to think more about this, because you now run into a problem of having to merge 3 arrays instead of merging 2 arrays. Merging 2 arrays is linear. Merging 2 arrays is linear. I presume that merging 3 arrays too will be linear in the sense that you can merge 2 arrays and then merge the second array. And since it's always 3, that's a constant factor. So you can assume that is also linear as well in terms of the analysis. But in terms of the actual speed, I'm not entirely sure it's going to be faster. You might need to try it out. That's the thing. But yes, that's also another way to solve it. And that's a very interesting question. Very interesting question. I like the question. But did I answer your question on the?
Yeah, you did. You did.
On the reduction.
I'll just try it out and see how fast it is, or maybe I'll make more research on it.
Yeah. Good. So that was a good question. Does anybody have any other question? Okay. So in terms of merge sort uses extra space, all right? But there's a way you can implement merge sort in constant space. But that's really out of our scope. I just put it here for completeness. So that's it about merge sorts. Now we are going on to quicksort. Quicksort is like merge sort. It's almost like merge sort. But instead of dividing the arrays based on the position, it divides the array based on a value. So essentially, it takes an array, selects a value in the array, and puts all the values to the left of that, all the elements to the left of that value to the left, all the elements that are less than that value to the left, and put all the elements that are greater than that value to the right. So by doing that, we divided the array into 2 parts, right? Now we can recursively sort each part and combine the results. Almost the same thing with merge sorts, but that's the distinction. The work in quicksort happens in the divide phase. The work in merge sort happens in the combine phase. So the fundamental question with quicksort you have to ask yourself is, if I have an array, can I partition that array around the value such that all the elements that are less than that value are to the left of the value, and all the elements that are greater than that value are to the right of that value? If you can solve that question, you solve the question of quicksort. If you can understand that, you've understood quicksort. That's the key thing to understanding. That's the crux of the problem you're trying to solve. Now, with quicksort, I didn't really get a lot of good visualizations that really shows what is happening. So I found this. I will come back to demos later. But so the thing here is, you have an array and you have a value. You are going to partition the array such that all the elements that are less than this value are to the left of it, and all the elements that are greater than that value are to the right. Now, when you do that, you have 2 smaller arrays. You can assume that this element in the middle is in the correct position. And this works because if all the elements to the left of this array are less, and all the elements to the right of this, so if all the elements to the left of this value are less, and all the elements to the right of this value are greater, that tells me that this value is in the correct position in the sorted array, right? This value is going to be in the correct position in the sorted array. And then if I can repeat the process and recursively sort the left and recursively sort the right, I can end up at my base case where everybody is in the right position in the array and they just return back up. So essentially what happens is it picks a random value. There are many ways to pick it. You could pick a random value, you could pick the first value, you could pick the last value. There are some nuances about which value you pick. And then once you pick a value, you partition the rest of the array to the left and to the right. And then you recursively sort the left and recursively sort the right. Now, the key thing to understand is, if you look at merge sort was efficient because we were dividing the array into equal halves each time, right? And if we didn't divide the array into equal halves and we're just reducing the problem, it would become inefficient because it becomes a straight chain and not a tree structure. Essentially, it becomes like a skewed binary tree. It's not efficient. Now with quicksort, the thing with quicksort is we need to make sure that our recursion divides the arrays evenly, or at least we try to divide it evenly for the most part for it to work. Now, this is getting into some complicated analysis, which I don't think we should go into, but I'll just mention it here for completeness that the element you select as your pivot is very important. The element, so the pivot is the element you are partitioning around. That's the value you are partitioning around. That element is very important. The reason is if you don't select the pivot well, you could result in a recursive structure where you just have a straight chain because you are reducing the problem one by one. I'll explain more in the visualization. So these are the recursive calls, for instance. So in the first line, in the first step, we picked 5 as a pivot, right? So what did we do? We put all the elements that are less than 5 to the left, and all the elements that are greater than 5 to the right. Now, this tells us that 5 is in the position in the sorted array. We recursively do that for the left and recursively do that for the right. Now, let's go to the left, right? We pick 3 as a pivot in this case. When we pick 3 as a pivot, we put all the elements that are less than 3 to the left, all the elements that are greater than 3 to the right. Now, 3 is in its position now. We do the same thing for the left of, so we do the same thing now for the left of 3, which we pick 2 as a pivot, and we partition around 2, and we result in this. We do the same thing for 4, but because 4 is a single element, we backtrack, we are done with that. Now we do the same thing for 1. 1 is a single element, we backtrack. So at the end of this line, we see that this element is sorted here. And we do the same thing to this gets sorted. So that is essentially what happens in quicksort. And it's called quicksort because it's very quick. If implemented correctly, it's the fastest sorting algorithm you can have. Fastest general sorting algorithm you can have. That is quicksort. That's how they call it quick. But the problem is you have to select the pivot correctly for you to be able to partition the problem into equal halves, or at least equal halves for most of the recursion. Because if you don't partition it properly, essentially you end up in a skewed recursive structure. You end up in linear recursion, basically, instead of tree recursion. And tree recursion is usually more efficient than linear recursion if you are dividing the problem, you are breaking the problem down. And in this case, because you are breaking the problem down, we want to use tree recursion and want to make sure the tree is as balanced as possible. Which brings us to the concept of balanced trees. Remember when we did balanced trees, if you have a balanced tree, then the height of the tree becomes log of n. But if you have a skewed tree, it becomes n. Essentially the same thing in this case. So how to partition? There are different ways to partition. I think I was thinking of going deep into this, but I don't think we'll have time to go into it. But essentially, there are different algorithms you can use to partition. There are many of them. So let's try and see what the demo says here. So for the demo, the issue with the demo is it doesn't really, unlike mergesort where it shows you the tree structure, this doesn't show you the tree structure in quicksort. So it selects the pivots. In this case, they are selecting, how did they select the pivots? Okay, maybe they selected the middle element as the pivot. And then they moved, so what they're trying to do is that they're trying to partition the array around this pivot they selected. But the way they are doing this is they're moving it to the end. And then they are looking for the first element greater than the pivot on the left, and the first element that is less than the pivot from the right, and then they're swapping them. So this element should be at the right of the pivot, right? So what they do is they know that they should swap this with this, and they keep doing that, right? So they organize all the elements to the left of the pivots and to the right of the pivots, and then they just put the pivots in the correct place. So you can see that now the pivot is in the correct place here. It's 509. And then they do the same thing for the left and to the right. So they do it on the left sublist. Pick 399 as the pivot, right? Switch it to the end of that sublist because we are only considering that sublist. And then essentially they try to reorganize the arrays by swapping the bigger ones and the bigger ones and the lesser ones around till they can put that element in its right position, which is in the right position here. And so on and so on. It doesn't show you the tree structure. So I don't think this really depicts it, but this is how it is. So if you continue doing that process, you get to a base case, and then you do the right as well, I think, and then you're done. Yeah. So quicksort is the most efficient sorting algorithm you can have. But if it's not implemented properly, it becomes quadratic. So let's look at the implementations here. Again, what are we doing here? If low is less than high, that means if we have at least 2 elements here, right? We partition the array around an index. Then we quicksort the left side and quicksort the right side. We call it recursively. So the work here is how do we partition the array, which they did here. Now, I won't go into this now. Maybe you can look that up, but there are many ways to partition the array. That's the kind of like, okay. So essentially, you can think of the problem like if I have an array and I have a number, can I rearrange the array such that all the elements that are less than the number on one side and all the elements that are greater on the other side? Then it becomes trivial to solve. Okay, so time and space complexity. The best and the average case is like merge sort because we have log n levels if we divide the problem well on each recursion. And at each level, we do O of n work to partition the array, which gives us n log n. But if we don't divide the array properly during recursion, we end up in n recursive levels instead of log of n recursive levels. And if the work done at each level is O of n, then our total time complexity becomes n squared. And that is where the difference between a balanced tree and a skewed tree is important. For the space complexity, the only thing here we are considering is the depth of the recursive call stack, which is O of n. If we partition properly. If we don't, then it becomes, which is O of log n, if we partition properly. If we don't, then it becomes O of n, because it becomes like a linear structure. Any questions on quicksort before we go? I know this is quite involved. I would say merge sort and quicksort are one of the hardest sorting algorithms to understand, especially quicksort. Go for it, please. Oh, okay. Maybe that was a mistake. So the best sorting algorithm you can ever have is quicksort. Quicksort is like the best sorting algorithm. Okay, go for it, Gideon.
Yes, so I wanted to ask, right? For the quicksort, well, I understand the fact that what's it called? I'm losing my chain of thoughts. Give me 1 minute. Yes, so the end is very crucial. We know the right end to select, right? So because if we use it has to be on the middle. So what if the largest number is on the middle then, right? So because you have to like everything just have to go to the left, then it's not more, you're not doing it like in two. And so how do we know what to pick? How do we know if it's like previous is there a way to know what to pick?
Yeah, so that's a very good question. And this becomes an open-ended question because there are many ways you can do it. And people have done research on this, on how to pick the pivot. I can tell you there are lots of papers online. People have done PhD thesis on these things. But I'll sum it up as this. If you always randomize your pivots, if you always pick a random value, right, you have a good chance, a very, very high chance, a high probability of having n log n if you always pick a random value. And that is kind of the best implementation. Because if you pick a certain value, right? So let's say you always pick the smallest value, right? Or you always pick the largest value. You could run into situations where that value you pick is going to be the worst you can ever have. But if you pick a random value, you are randomizing it so that sometimes your truth will be balanced, sometimes it will not be balanced. But if you look at the entire thing, it becomes more like a constant factor over n log n, not necessarily changing it to n squared. But the crux of the matter is you have to divide the problem into equal halves for most of the time. Now, quicksort is, so because of this, this brings us to what we call probabilistic algorithms, in that your algorithm behaves funny based on different inputs, because if you do it in a randomized way, right, you are guarding yourself against any input that could be submitted. Because let's say you pick the smallest each time. If someone gives you an array that is sorted, then they spoil your algorithm because it becomes n squared. If you pick the largest each time, if someone gives you an array that is sorted, they also spoil your algorithm. That's the thing. So you want to ensure that you randomize it most times. Now, there's an algorithm they call median of medians, which is kind of the most efficient in that. So the thing is, we always want to pick the median. In the best case, we want to pick the median. Because if you look at 5 is the median of this collection, of this array. Because if you take a collection and you sort them, the median is always going to be in the middle, right? So you always want to pick the median. So there's an algorithm you can use to always select the median that is always correct, which I can share later, but that algorithm is too complicated for anybody to ask you in an interview or anything. If anybody asks you that algorithm in an interview, then you don't work for that company. But the thing is, no, you don't ask such. No, you don't ask such. If anybody asks you median of medians, because this is an algorithm that PhDs, not one PhD, like I think 3 or 4 of them, you were the ones that came up with it. So the truth is, you're not going to come up with it. So it's on your own. Like if you read it and memorize it, it's fine. But coming up with it on your own is almost impossible. Because one person didn't come up with it. So like 3 or 4 people that came up with it. And that's kind of the most efficient way. And if you look at the implementation looks inefficient. But when they did the analysis, mathematically, so that it was efficient. So that's why I said that area is very complicated. But for just our own basic stuff, if you want to do it, you always pick a random value. With the random value, you're always going to be fine. But if you want to be exact, you can look up median of medians.
Thank you.
Yeah. Isioma, go for your question.
Thank you very much. So I have 3 questions to ask. First question is based on this pivot element, right? So I'm thinking programmatically now how you can write a program that picks up a random value. How would you typically implement that? Like what index, and that's one. Second question is, I don't know why, or is there a way to check if an array is already sorted so that you don't even try to sort something that is already sorted in the first place? Right? That's the second one. And then the third question is about the last sorting technique that you talked about. Try not to lose my train of thoughts. But if you before I just got it now. If you have an array that has an odd size, since I think I remember you talking about dividing it evenly, right? Especially when you want to do the merge sort so that you keep dividing. Like I have an array size of 4, I divide it into 2, and then I divide the 2 into 2 till I get to 1. So if I have an array or an input array that has an odd size, how do I, is it that candidate, like for you to implement a merge sort, the array has to be evenly, it has to have an even size, or what? Those are my questions. Thank you. Sorry.
All very good questions. Let me start from the first question. I hope I still remember. So the first question you asked was, how can we write an algorithm to always pick a random element, right? So what you could do is, ultimately, you're looking for a random index. So there are functions you can use to generate to give you a random value between a certain value and a certain value. So if you put in those two to that function and you get a random index, you can use the element there as a random value. So essentially, it reduces to giving an array, how can I find a random index? And finding an index in an array is easy because you just have the left and the right each time you are recursing. So you just put the random between the left and the right. Does that answer the first question?
Okay, so essentially we have to implement a function that generates a random number with the size of the array.
Yes.
Okay.
I believe there are libraries that you can use to get a random value in one line.
Yeah, sure.
Yeah. Then the second question was, I don't remember the second question. What was it taking? Remind me.
So the second question was about
You said, is there a way to know if
Okay.
it is sorted, so we wouldn't even bother sorting?
Okay, I remember now. So yeah, so this is, so what the thing about this is, the only way you can know is if you check. Some sorting algorithms reduce to best case of O of n if it's sorted, but most of them do not. So you could just check if it's sorted in O of n before sorting it, if it's not sorted. That's one way to do it. And that is O of n plus O of n log n in worst case, which is still fine. So the only way you can know is to check. Short answer to your question. Does that answer the second question?
yes, it answers.
Okay. Now, for your third question, you can sort an even array or an odd array. Essentially, what happens is it's going to reduce to an array that has 3 elements. So it reduces to an array that with 3 elements that will have 2 recursive calls, 1 to 2 elements and 1 to 1 element.
I'm sorry,
That's what is going to happen. So if you have an even structure, right, you are going to have a recursive call that will have 2 and 1, not 2 and 2. Does that make sense?
I thought, for example, we have an array with size 8. We divide it into arrays of 4, 4. We divide it into 2 arrays with a size of 4 each. Then those 2 arrays get divided into a size of 2 and then 1. Right?
Yes.
In methods. But if we have an array that has a size of 7, how do I divide that?
So what will happen is it will get divided into 4 and 3. It's not going to be divided evenly. So usually the algorithm to find the middle, which is kind of the middle, usually biases you to, let me see, 0, 8, 2, 4. So it usually biases you to the left side. The left side usually has more values than the right side.
Okay.
So let's say you have your left is 0 and your right is 7, right? You do 7 and you divide it by 2. But you do an integer division, which is 3. So 0, 1, elements 0 to 3, which are 4 elements, to be on the left. Elements 4 to 6 will be on the right.
Okay.
If that makes sense. Yeah. So the division takes care of that. So your tree will end up with, you have a balanced tree, but then you have one level that doesn't have the same level as the others, but it's still fine. It's still balanced.
All right. Thank you.
Okay. So any other questions? At this rate, I don't think we'll be able to go through all what I planned for today, but I will try and move as fast as possible. So merge sort is the best sorting, quick sort is the best sorting algorithm you can have. And they are the most efficient sorting algorithms. Merge sort is good in that you always guarantee it should be n log n for best average and worst cases. Quick sort is n log n for best and average case, but n squared in worst cases. But from our perspective, honestly, you really don't care. Because I just want to be using whatever your sorting algorithm, your sorting library uses. And most of them are efficient to give you n log n. They use a combination of both. I think C++ has a stable sort that uses quick sorts. And then the other sort uses merge sorts. So there's some certain terminology you come across. There's in place, which is if you use extra space, and there's stable. Now, being stable means when you have equal elements, you they keep the same order after sorting. Now, for numbers, it's not the same thing. 4 is 4. But when you are comparing like objects, it may not be the same object in memory, and that decision becomes important. So quick sort is stable, merge sort is not stable, which is why the stable sort in C++ is quick sort. So this is another variation. So I'll just speak through this. These ones are just variations that I just think you should know. Bucket sort is a divide and conquer one, but in this case, you are dividing the array into any number of buckets based on ranges. So you are taking the array, dividing it into separate buckets, sorting each bucket, and combining the results back. You can look at the demo and the code later. Time and space complexity for bucket sorts. So when you divide the item into the bucket, it's O of n. When you sort each bucket, it depends on the algorithm you use to sort each bucket. You can use any algorithm to sort each bucket. And then when you combine the result, it's O of n. So that really depends on what you use to sort the bucket. And space complexity is O of n because you have to create the arrays, put the arrays in new buckets. The items in new buckets, sorry. So that's divide and conquer. Now, the other problem-solving strategy I want to discuss is transforming the problem. So sometimes we can't divide and conquer the problem. In this case, we can. Sometimes you can't divide and conquer the problem. Most times you can decrease and conquer, but it might not be very obvious. But you can also think about how can you change the problem to something else that you can understand. You see the thing? So the thing is, I can transform the problem to a different representation. And then I solve the problem. But the catch is, when I transform the problem, something has to give. Either I incur extra time to transform the problem, or I incur extra space to store the structure I'm going to use to store the problem, or both. But something has to give. So the way you can think about it is that, so you think about all the possible data structures and how if they can help you solve the problem. So you think about arrays, linked lists, stacks, queues, decks. So in the context of sorting, for sorting algorithms, right? Sorting an array, the input problem is already in an array. So there's nothing really an array can help us with. With linked list, the input problem can be in an array or a linked list. So nothing can be done there. But can we use stacks? Is there any way we can put the elements in a stack and get it sorted? Is there any way we can put the elements in a queue? So these are the questions you ask yourself when you're trying to transform the problem. Can you use hash tables to transform the problem? Can you dump the elements in a hash table? Does it make your life easier? How about put the elements in a tree? A balanced binary set tree. So if we do an in-order traversal in a binary set tree, we get a sorted order. So that tells me if I can put all those elements in a balanced binary set tree and I do an in-order traversal, I'll get a sorted order. So binary set tree can work. A binary heap always gives me the smallest value. So if I dump all the elements in a heap and I keep taking the smallest value, I will get my results. So that can work. How about if you represent it as a graph? PFS, DFS. So these are questions you ask yourself when you're trying to transform the problem. You see the thing? Now, when you're reading all this algorithm, they don't really tell you that this is the rationale behind it. But this is kind of what they're trying to do. They're just trying to look for ways to solve the problem. So let's start with an array. Array and lists is already used to represent the problem, so there's nothing we can do. So let's see stacks. If we dump all the item in the stack and we remove all the items from the stack, it's not really going to help us because the stack is last in, first out. Maybe we can insert it in another order. Maybe we can insert the items in sorted order in the stack. Maybe. Yes, that's possible. So if we want to insert, so let's say we push 1 to the stack, right? And we'll push 3 to the stack. If we want to push 0 to the stack, we have to pop 3 and 1, put 0, and push 1 and 3. That becomes O of n for each push in the worst case. And if we do n push and n pops, we're going to have n squared. So that doesn't really help us. Essentially, that becomes the variation of insertion sort. Essentially, that's what it reduces to if you try and use a stack to solve the problem. Can we use a queue? Maybe we can insert the item in some sorted order in the queue, but if we just dump it into the queue and we get it out, we are not getting the sorted order. We have to. Each time we enqueue the item, we have to insert in sorted order. Or we can dequeue it and insert in sorted order when we are dequeuing. But the problem is, we are going to do O of n work n times, however we look at it. And it's still going to give us O of n squared. So essentially, it's a variation of insertion sort. If we look at decks are similar to stack and queues. So we most likely get the same result. So the reason why I'm going through this is just to understand the problem solving strategies when you're trying to like solve a problem. How to like approach problems. Now, but I know that in a balanced binary set tree, if I dump all the items in a balanced binary set tree, balance is the keyword, and I run another traversal, I will get the elements in sorted order. So that's one variation of a sorting algorithm. But what's the catch? I need to use the binary set tree. I need to incur extra space. So the thing is, tree sorts. So let's look at tree sorts. Oops. What is happening? Oh, my account is not logged in. Okay. 1 second. Let me temporarily stop presenting so I can log in. I will share once I log in. Okay, there we go. Perfect. Okay. So if we are able to get a balanced binary set tree, we know that if we do another traversal, we will get a sorted order. So that's essentially what we can do. Construct the binary set tree, which is just inserting all the items into the tree. And to insert each item is log n. To insert n item becomes n log n, which is still fine, not too bad. And if we do another traversal, that will give us O of n, which is still fine. So we're good. So this goes back to another traversal. I don't think I need to go through this because we've discussed another traversals previously. So I don't think we need to really go through it, but essentially that's how it works. Exactly on how we can use a tree to transform the problem. See now, the problem is still the same problem. We just introduce the data structure to simplify the problem. Now you might say that okay, it incurs extra space, but O of n extra space is not too bad if I don't have any better solution to it. So inserting n items into the tree is n log n for all the insets. Running another traversal is O of n. So total time complexity is O of n log n. And the space complexity, because you are storing all the elements in the tree, is O of n. You're taking extra space. Now, what about the heap? This is how we came up with heap sorts, essentially. You can think of it like putting all the items into a binary heap, and then you keep removing the smallest item. Because remember, excuse me, in a binary heap, you only have access to the smallest item. So if you keep removing the smallest item, and you move everything from the binary heap, you will get your answer. So the question now becomes, what's the time complexity to insert an item into a binary heap? It's log of n, right? If I'm putting n items, all the items in a binary heap, n items, that becomes log of n log n. Sorry, n log n to insert everything. What's that complexity to remove everything from the binary heap? Removing one item is log n. Removing n items is n log n. So n log n plus n log n is still n log n, which is fine, which is not better than merge sort or quicksort. Now, empirically, it's slower than merge sort and quicksort, but in terms of a complexity analysis, it's still acceptable. Now, in this case, in sorting algorithms, you have better algorithms, but sometimes you don't have a better algorithm, or you can't find a better algorithm within the time frame. So you can use things like this to help you see how you can go about it. Now, with heap sort, and I think we did heaps previously, so I don't think I'm really going to this, but the thing about heap sort is you would instead of creating a new heap, because a heap is represented as an array, they use the array itself to behave like a heap. And then they call heapify on the array to create a heap. Then they keep reducing the heap little by little till they take all the items from the heap. So I'll explain here. So this is your array here. What they are doing here is they are. So if you look at the heap, right? If you take the array and construct a heap, this is what you have. You have this this structure. If you construct a heap, but this is not yet a heap, so they need to heapify it. And I think remember how to heapify where you start from the elements and you move them up and down successively. Essentially, I won't really go into that, but that is what we are doing here. So the last item is already in a heap because it's the only item, right? The second to the last item is also in a heap. This 8 here is also in a heap because it's the only item. Essentially, we keep going till we get a tree because you need children before you can merge two heaps together. So what you're doing is that you're merging two heaps successively. I'll explain what I mean. So when we get to 9 has no children, so there's nothing to do. 10 has no children, there's nothing to do. 6 has no children, there's nothing to do. Now, but when you get to 5, right? 5 has 2 children. And each of those children are heaps of their own, or in their own right. Now, when you now want to merge the two heaps together, that's where you now determine which one is. So in this case, you are looking for you create a max heap in this case. So we take the bigger value and put it up. So now that's what we do. We take the bigger value and put it up. And it's important to understand that the bigger value is going to be either of the 2 children I have, because the 2 children are heaps in themselves. So it's guaranteed that those children are the biggest value they can have in their subheaps. That's why it's correct. I'll explain going forward. So now we see that we swapped it. Now 8, 5, and 1. This is the max heap. Like this satisfies the constraint for a max heap. Now we can agree on that. Now we continue to 2. When we get to 2, right? 10 and 9 are heaps in themselves. So we merge them together by picking the biggest value and putting it up. And then we take 10, put the value and put it up. And then if we had children, we have to move 2 down to the respective position. So we have that. We go to 3. Now with 3, it becomes interesting. We want to merge the left heap and the right heap, right? So because the left heap is a heap, the left child is a heap, and the right child is a heap, I'm guaranteed that my children are the biggest values I can find in that of 3. Because if you look at it, 8, 5, 1 is a heap. And because it's a max heap, right? And 8 is the root of that heap, which is a child of 3. It's guaranteed that there is no other element that is greater than 8 in the subtree. That's why it's correct. So we keep moving that. We come to 3. We take the bigger value between our 2 children heaps and put it there. Now, we now need to move 3 to the right position by moving 5 to where 3 is. Now, when we are done with this here becomes a max heap. So you can see how we are building the heap successively. Now, when we go back to root now, because the left is a max heap and the right is a max heap, we can merge the two heaps together. So essentially, that's what heapify does. It takes heaps and keeps merging them successively. And you can merge a heap successively in log of n time. Now, heapify operation is O of n. The reason why that is O of n is very complicated. You expect it to be n log n, but it's O of n. And it's O of n because most of the work you do is from half of the array. I'll talk more about that later. Let's finish this. So we get back to the roots. And now when we are at the roots, we need to merge the left heap and the right heap. Both of them are heaps. So I'm guaranteed that the biggest value is going to be one of those children. And if you remember the very invariant of a heap, what a heap specifies, it says that every child is either less than this value or greater than this value, depending on if it's a max or a min heap. Like this is a max heap. 5, 3, 1 is a heap. I'm sure that all the children of 5 are not greater than 5. This is also a heap, right? There's no value in this subtree that is greater than 8 because it's a max heap. And let me see. And then we go forward and then we take 7. Because 10 is bigger, we put 10 to the roots. And then we put 7 in the right position by swapping it with the bigger of the 2 children, which is 9. Now we have a max heap. So that heapify process created the heap from an array. The reason why we do this is that we are trying to do it in place. We don't want to have to allocate space to create an extra array as a heap and add it to the heap. You could do it that way too, just that you create extra space. So when you are now done with that, you now start beginning to remove. So the next thing to do now, you want to remove the smallest item, right? The first, you want to remove the item at the top, which is the max item. So essentially, they remove the biggest item in the heap, right? And they swap it with the last position. Essentially taking it out of the heap. And then they heapify what is left by moving that to the right position in the heap. So that's essentially how heap sort works. If you really understand how, if you understand how heapify works, and understand how to insert in a heap, then you should be able to understand heap sort easily. But one way to think about it, if it's a bit too hard to grasp, is that you're essentially dumping all the elements in the heap and removing them from the heap. That's the easiest way to think about it. Once you can think about it that way, you can work backwards from there. So again, it's n log n total time because it's n log n to insert everything and n log n to remove everything. So now there's another variation here called counting sort. So if I use a hash table to keep track of how many items an element occurs, right? I can do something there. So I can create a hash table and count all the elements, right? And if I know the minimum and the maximum, I can look through the minimum and the maximum and insert their counts and insert the amount of times they occur in the hash map into the array successively. So I think a demo is the best place to show this, really. This is counting sort. Yeah. So for counting sort, essentially, let me create a smaller one. Okay. Let me just sort it. So what they're doing here is they are creating buckets. They are creating buckets here, and they are not buckets. So they are counting the amount of time each element occurs. That's what they're doing here. So this here is not really aligned, but ideally it should be aligned to the graph. So they count the amount of time each element occurs, and they just remove it from. They just loop through and move it successively to add to the end. That's counting sort. But essentially, what are you doing? You're transforming the problem by using a hash map or an array. So what's the time complexity? It's tricky because you have to know the max and the min. And because you have to loop through the max and the min, you have to add it to looping through the entire array, which is max minus min. And max minus min can be big. If let's say your min is 0 and your max is 10 million, then that's very bad. So this is just about it. So there's another type of sorting that is also important. It's called a topological sort. Now this is using a graph. You can actually use a graph to do sort. And that's what they call topological sort. Essentially, what you do is you build a directed graph of items. And then you run DFS and BFS on the graph. Now, from a sorting perspective, it's not efficient because to build the graph, we need to build it in O of n squared time. But the real use case for topological sort is to model dependencies in the real world. What do I mean? So let's look at the demo here. I think this is not a good edit graph. No. Let me pick a simple graph. Okay. Yeah, this is a simple graph. So essentially, the arrows mean that 0 depends on 1, 1 depends on 3, 3 depends on 4, 2 depends on 3, 0 depends on 2. So you can think of it like modeling dependencies. Like, let's say you want to model dependency of actions that can happen successively. Like, this must happen before this, which must happen before this, which must happen before this. So those of you that are familiar with build systems, like when you are building something, right, and you list your dependencies, it's essentially what you do. Like Maven and what do you call it now? Maven and other build systems. This is what they do. They essentially enumerate your dependencies and build a graph, and then go through the graph and then run through the graph when they are building. So essentially, that's what the topological sort is. So there are different versions, but the long story short is if you do a DFS or a PFS on a topological sort, you will get an ordered version. So let's look at the DFS version. So with DFS, we start from 0, for instance, and then we go through 1 to 3, and then to 4. Now, when we get to 4, we're done because 4 has no neighbors. So 4 is done, and it finishes. So you can add it to your results. When you get to 3, 3 is also done. You can add it to your results. 1 is done, you add it to your results. From 0, we need to explore 2. So we need to explore 2, add it to the results, and then come back to 0. So the key reason why this works is because you explore all your children before your parents. And because it's a directed acyclic graph, meaning that there are no cycles, right? Your DFS or BFS will give you the topological sort. But with BFS, you need to modify it slightly. Maybe you can go over that. It's called Kahn's topological sort. But essentially, it's a variation of BFS where you start from where you want to start from. Like, so you start from a node that has no incoming edges. That's what you do. Because if you look at 0, 0 is the root, and 0 has no incoming edges. That means you can start from 0 to do whatever you want to do. You can't start from 1, you can't start from 2, you can't start from 3, you can't start from 4. If you need a DFS, you would start from 1. You explore 1, 3, and 4, right? And before you explore 0, so it will work. But with BFS, you need to start from the element that doesn't have any child, any incoming edge. So once you do that, you add it to your results and remove that element from the graph. Then you select the next elements that don't have incoming edge, which is 1 and 2. Remove it from the graph. So remove it from the graph like that. So if you keep doing that, you get your topological sort. So yes, you can do, for sorting algorithms is not efficient, but you can do topological sort. So what's the time complexity? You need to build a graph, which can be very expensive depending. Then you can run DFS or BFS, which is O of V plus E, which is vertices and edges. So the topological sort itself runs in V plus E time, which is linear, which is fine. But building the graph can be expensive. It can become quadratic, depending on how they give you the graph. But if the input is already given to you as a graph, then topological sort is efficient. So how do we use topological sort to sort numbers? What we can do is we could build a graph of every other item, of their relationship to each other. So you look through, if a number is less than a number, you create a dependency. So if you do that for every pair of numbers in the array, and you run a topological sort, you will get a sorted order. But building that graph in itself is O of n squared, which is why it's not efficient. Okay, so I know that was a lot, and honestly, I was looking for the best way to try and go through this thing because it's really, really a lot. And before we go to problem solving, does anybody have any question? Okay, are we tired? Do we want to go through problems or do we want to call it a day? I mean, they're on the slides, so you can still go through them. Should we go through the problems? Thumbs up or thumbs down? Okay, cool. So for problem solving, what is the key takeaway from all this? You're not going to implement the sorting algorithm. No. But why are we learning it? To know the problem solving strategies. So the first thing you try to do is try to solve the problem in the most basic way without too much analysis, which is the brute force way. Then see if you can chip away at the problem or build a solution incrementally. Now, most times, you can solve a problem using almost all these approaches. But the problem is they will not be efficient. So you're also looking for the efficient one when you're done. Then see if you can reduce the problem into smaller subproblems and combine the results. That's divide and conquer. Binary search is like divide and conquer. It's just that you go to one side. Or you can call it divide and conquer, decrease and I'll say it's decrease and conquer, sorry. Binary search is decrease and conquer. Then if that doesn't work, you brainstorm through all the data structures you can see and see if you can apply anyone. Just brainstorm to data structures and see if they work. You estimate the time and space complexity of each and decide when you want to go with. So this is kind of like a general problem solving tip you can use. So I'll go through the exercises. So this code sorting explore card is fine. I will say just read the editorials and solve questions you find interesting. Then go through topological sorting and then watch these topological sort videos. And then for the resources, I put some resources here. Code interview patterns is the best in terms of mastering the patterns. And then for visualizers, I put all the visualizers here. And the sorting visualizer has the code for all the sorting algorithms. So you can go through that in different languages. Questions before we go back to problems? Okay, so just as a caveat here, I'm just going to go through the problem and try and go through different approaches we can solve it. I'm not actually going to be solving them. It's for the sake of time. Right, so let's get started. So for the kth largest element in an array, so the question is saying you have an array. You want to find the kth largest element. Could be the first, could be the second, could be the third, could be the fourth. What do you think is one straightforward way to solve this? I mean, if you sort the array, you can get the kth element, right? Sorting is the most trivial way. Sorting is the most trivial way. Yep, exactly. You can use selection sort, you can use insertion sort, quick sort, whatever sorting algorithm. Just sort it and pick the most trivial one. And pick that's the most trivial way. But there's a way you can, like I said, there are better ways you could do this. So let's think about it. What can we do here? What is the brute force way? Okay, the brute force way is probably to sort because we know we can sort. But let's say we didn't know what sorting was. What would we do? Well, we'll have to go through the array and find the first element. And then go through the array and find the second element. And then find the third element. And then find the fourth element, which will be n squared. We'll know we can sort in n log n. Right? Okay. So sorting is there. Is there any way we can decrease the problem? Like, so let's say I have this array and I reduce it by 1. Can I reduce it by 1 and then add my results to the array? In this case, nah, unless I really have the positions to begin with, because I'm looking for the positions of those elements. So that doesn't really work, right? Here, if I use a hash map, that's an interesting one. So if I dump everything in a hash map, right, that could work. But then how do I know the case position in a hash map? The hash map is not sorted, remember. That means I have to loop through either from the maximum to the minimum or the minimum to the maximum, which, depending on how big the maximum and the minimum is, might be very, very terrible. In this case, we can go from minus 10 to the 4 to 10 to the 4. So that's 10 to the 8. That's a bit too much. You see the thing? So that doesn't work. Decrease and conquer. What of divide and conquer? if I split the array into multiple halves, right? Is there any way I can combine those values to find the kth element? Wait, if I build a heap, if I I know I can merge two heaps, right? And I know a heap can always give me the largest element. We'll come back to that. That's one way. But so looking at it with divide and conquer, and I'm going to be honest here, divide and conquer algorithms are difficult to find, especially if you are doing it the first time. Usually, decrease and conquer is more straightforward. Divide and conquer is difficult to find. My intuition tells me there's going to be a divide and conquer solution to this problem, but I don't think I'll be able to figure it out within our time frame. But there might be a way. I'm not sure. But okay, so let's move forward. Let's see, can we transform this problem into something else? We know that if we sort it, if we change the input by sorting it, that will work. If we dump it into a stack, does that help us? No. Dump it into a queue, does that help us? No. Dump it into a hash table. It can help us, but it might be very bad. A binary set tree, definitely. If I insert all the items into a binary set tree, but then can I get the kth element in a binary set tree? That's not very easy. Because then I have to go through all the key elements, all the first key elements, which reduces to O of key. Not too bad. I could do it with a binary set tree and keep removing the largest element, or do a reverse in order traversal to get the kth position, or an in order traversal to get the n minus kth position. That could work with the binary set tree. Yes. But let's keep going. What of a heap? A heap always gives me the minimum or maximum value. If I dump all the items in a heap, I can get the maximum value. If I keep taking out the maximum value k times, I can get my kth value, which will give me what is complexity there. Dumping everything to a heap would be like n log n plus removing key items from the heap plus k log n, which is n log n plus k log n, which is kind of n log n in a way, which is equivalent to sorting. So you can see there are different approaches here, and that's giving me a starting point. Right? So with all these ones now, we find an n log n algorithm. But it's possible that there's still a more efficient solution. Right? Now we've brainstormed, look at the process. We started with brute force, right? Which is just to select it first. Then we tried to decrease and conquer, which was essentially like almost like a session sort in a way, which is almost like brute force. We didn't work. Divide and conquer could work, but not trivially. In that we could assume each of them are heaps and keep merging the heaps. But then we could just use a heap to begin with. So that's not really very efficient. So you can see the different approaches we look at to try and solve this problem. Now, the way you might go about it might be different from the way I go about it. It's not really, it's just the important thing is to try and go through different approaches and practice with them. Now, it turns out that because you are looking for the kth largest element, right? I could use a heap, definitely. But okay, a divide and conquer algorithm just came to my mind now. I'll talk about it later. But I could use a heap here, definitely, right? I could use a heap here. So what you could do is dump everything to heap and remove it. But is there any way we can use the heap without dumping everything to the heap? We just need the kth largest element, right? So what if the kth largest element is at the top of our heap? So what will it take for the kth largest element to be at the top of our heap? The kth largest element is the smallest element from that item to the end of the array. So for my kth largest element to be at the top of a heap, of a main heap, right? It means that So for my K largest element to be at the top of the heap, it could either be a min heap or a max heap, right? So if it's a min heap, it means that all the other elements in the heap are smaller. Right? That's what it means. If it's a min heap. Sorry, I got that wrong. If it's a min heap, it means that all the other elements are greater. If I'm at the top. So if I'm at the top of a min heap, that means I'm the smallest in the heap. Right? That means all the other elements are bigger than me. If it's a max heap, I'm at the top. That means I'm greater than all the other elements. So that tells me that if I use a max heap to store the n minus k smallest elements, I will get my answer. Or if I use a min heap to store the k largest elements, I'll get my answer. So that's one way you can have an efficiency on this, by using a heap to keep track of, not the full heap. Now, why it becomes important is because your algorithm will now run in log of k, in n log of k, instead of n log of n, because you're only storing k items. Or if you store n minus k items, it runs in n log of n minus k. However you want to think about it. But that's an efficiency about it. So the thing is, so with that now, I know that, okay, that's one solution, which is an improvement. But then, if you are looking for the kth largest element in an array, right? So let's say we sort the array. Can we know the index the kth largest element should be if we sort the array? That's the thing. It's not trivial, because so if we sort the array now, so k is 2, right? In this case, we are looking for the second largest element, which is 5. If we sort this array, 5 will be in the second to the last position, right? But if we look at the second array, we are looking for the kth largest element, which is 4. If we sort that array, 4 will be in what position? 6, 5, 5, 4. Is it the k to the n position? The fourth largest element. Okay, yes, it is. It is, yes, it is. So that tells me that in the sorted position, my kth largest element will be at position n minus k. Right? Is that n minus k or n minus k plus 1 or minus 1? Not sure of the specifics. But I know that I can get what index my element should be in the sorted array. Now, from quick sort, I know that when we used to do quick sort, remember we are partitioning items around a pivot. Now, if I randomly select an element in the array and I partition all the elements around that pivot, right? That pivot is in its correct position at the sorted array, right? And I know the correct position of the index I'm looking for. So if I get that pivot number and I see that it's less than what I'm looking for, I can just do my quick sort to the right and keep doing that till I get my answer. Now, but because we are not doing the recursion on both sides and it's recursion one way, it's kind of like almost like binary search, except that we are doing n work each time. So which reduces to n plus n over 2 plus n over 4 to 1, which is O of n. So that gives you O of n here. But that algorithm is kind of complicated to come by normally. It's not something that you'll be expected to come by. But I'm just illustrating it to show like different ways you can solve the problem. So you could sort, you could use a heap, you could use a min heap, you could use a max heap, you could use quick sort for this problem with different efficiencies. The quick sort is a bit hard to implement. So this is just, I would like to go through problem solving. So I think the way I solved it here was using a heap, right? Let me see. I think I solved it here using a heap. Yes, I solved this using a heap. So essentially, I just used the heap. But I didn't dump everything into the heap. I used a min heap, right? And I dumped the k largest items into the main heap. Now, because I'm looking for the k largest item, if I have the k largest items in the main heap, the k largest item will be at the top of the heap. Right? Now, but the thing is, as I'm looping through, I can remove the items that don't fit into the heap and not consider them at all. And if they do, I push them in and remove the top continuously. So that's essentially that problem. Any questions on that? Okay. So you see how this k largest, top k frequent, k closest, they are the same pattern. They follow the same pattern. Somehow. When you see top k, top this, a heap is there. You can either use a heap, you can use quicksort, you can use any of those things. So for the top k frequent elements, what are they asking for? Given an integer array, return the k most frequent elements. The k most frequent elements, the ones that occur. So now we are looking for the kth value, but the kth most frequent. So if I count the frequency of the elements and I sort them, right? I will get my kth most frequent element. So based on that, I can apply all the approaches I talked about the other time. Let me see what this was. Okay, this was using a heap too, yeah. I think it was using the heap, yeah. So what was this about? Yes, so I used the heap to counted it, and then I used the heap to like store. I think it was a main heap. I used a main heap to store the what they call it now, the k most frequent elements, and then the k most frequent elements, and that's what they're asking for. Essentially, they're looking for the k most frequent elements, and then so just return the value in the heap. Let me see. That solution is still here. Yeah. So just return the value in the heap here. Just return the value in the heap. So k closest points to origin is a variation of the same problem. They are saying, given an array of points where you have it on a plane, find the distance between 2 points is this. Return the k closest points to the origin. So it's kind of like saying the k closest points to. So you can reduce this problem to, okay, they're asking for k closest points to the origin, right? So that means I have something. I have to have a notion of distance. So if I can compute the distance to that origin, and I have them in an array, right? And I'm looking for the k closest points. If I sort that array, right, the minimum of that, the k minimum elements are my k closest points. Which is essentially the same thing here. So you could use a heap, you could use sorting, you could use min heap. I think we use min heap or max heap, depending either of them or both of them. And then you could use quicksort as well, quicksort style, or finding the partition around the pivots. So these k problems are mostly the same thing. So for this one, the third maximum number. Okay, what they're asking here, they're saying return the third distinct maximum number in this array. If the third maximum number doesn't exist, return the maximum number. So if I sort it right, I can get the third maximum number, right? Third distinct maximum number, not the third maximum, third distinct maximum number. So if I count, so that means I need to like, so just looking at it, if I put all these items in a set, if I remove duplicates, right, and I sort it, I'll get my answer. The third value from the end is my answer. If I remove duplicates and I sort, third value from the end is my answer. That's one way you could do it. Yeah, that's one way you could do it, essentially. I think there's a more efficient solution that you could keep track of the first, second, and third as you scan through it. That's another way you could do it. So let me see, sort colors. Okay. So it's saying given an array with norms with n objects colored red, white, blue. Red is 0, white is white, blue is 2. Sort them in place so that the objects of the same color are adjacent with the colors in the order of red, white, blue. So use integers to represent the colors, and you must sort the parameter using the sort function. So they want us to sort this without using the sort function, essentially. They want us to sort it, which is kind of like, so if you think of quicksort, what are you doing in quicksort? You are putting elements that are less down to the left, elements that are greater down to the right. Do you see any similarity here? So let's reduce the problem. Now we have 3 elements. Let's say we reduce the problem to, so now we are considering 3 elements. It's too much. Let's decrease the problem. Let's put 0 and 1 together, and let's put 2 alone. So giving 2 values, right? Can I partition them in an array such that one value is on the left, one value is on the right? I think that is trivial. So if I do that, if I break it into, instead of 3 values, I have 0 and 1 on one side and 2 on one side. Then when I'm done with that problem, I could go solve the 0 and 1 problem because that's those 2 left. You see how that helps to break down the problem? So I'm going through this because these problem solving strategies are kind of things you just try and look out for all these problem solving strategies where you're solving problems. Sometimes they may be there, sometimes they may not be there. That's the thing. So in this case, I know that if I do that, it will work. If let's say I don't know how to partition 3 numbers across 3 numbers, but I know how to partition across 2 numbers. So I do it to 2. So let's say they give me n numbers. I can't partition n numbers, right? But I know I can partition. Maybe I can partition n minus 1. Maybe I can do n minus 2 till I get to 1. But now I can partition 2 numbers. So I keep doing it till I get to 2. The partition 2 numbers and I turn the result up. That's it. That's the strategy you can use for this. Now, there are other ways you can use with 2 pointers and swapping. I think you can use 2 pointers for this as well. But this, I'm just trying to look at different. So if you look at it now, can we throw this in the heap? Maybe we just need to count the occurrences. Maybe if you count the occurrences and then we populate them to work, but then we incur extra space. So we can just count the occurrences, right? 0 occurs 2 times, 2 occurs 2 times, 1 occurs 2 times. And then we'll populate the array with the occurrences. That's a very straightforward way to do it. But then we incur extra space. It's not constant time. Yeah. So I think there's an efficient way to do it in constant time, though. There is a way to do it in constant time. Yeah. But again, sometimes you may not get the efficient algorithm right off the bat. So let's see, course schedule. So essentially, this is saying that you have a number of courses you can take, and you have the courses and you have prerequisites you have to meet. So some courses must be taken before some courses. So they are saying you should return an order in which you can finish the courses. So this is a specific example where you can apply topological sort in this kind of problem. Essentially, you just need to build a graph. And I think you can apply topological sort to this, yes. Let me see. Course schedule is almost the same thing. So the truth is, all these other problems are topological sorts. They are all topological sorts, most of them. This course schedule is almost the same thing, but it's asking if you can finish all courses. So essentially, it's asking if there is any cycle in the graph or not. Because in a directly cyclic graph, there are no cycles. If you have a cycle in a directly cyclic graph, then it's not a directly cyclic graph. Topological sort, we went over topological sorts in the lecture. So it means it's a way of modeling dependencies as a graph and then running a DFS traversal over the graph to get a sorted order. I'll go over it once I'm done with this example. I'll just recap it. Maybe I should do that now. I think it's the best time to do it. So a topological sort essentially is building a directed graph of items and they're running DFS or BFS on the directed graph. Now, I made a mistake. So it should be a cyclic graph, not just a directed graph. A directed acyclic graph. That means a directed graph with no cycles. So, but the issue with applying topological sort to sorting algorithms is that building a graph is expensive, which is O(n) squared. So it's not very efficient for sorting algorithms. But in the real world, we use it to model dependencies. So a classic example is you have a set of tasks you want to do. Like you have this task, you have that task, and that task. And then you model them as dependencies. That's okay, this task depends on that. This depends on that. This depends on that. So if you model all those things as a graph, when you want to run the tasks from beginning to end, right? Whatever is executing those tasks, we run a topological sort on the graph you built from the model you created, from dependency chain you created. And then it builds a graph, and then it runs a topological sort on the graph using DFS or PFS. So like Maven build systems, they use all these things under the hood. Like Maven for Java, the build system, using that under the hood. I'm trying to think of a real world example that uses it. Maybe you are familiar with is step functions now. These step functions in the cloud. I think AWS step functions using something like this too. But they're applicable everywhere. So in this case, the question here was asking us that if you want to take courses, right? How, and you have some prerequisites. Let's say I have to take course A before course B, and course C before course B, and course A before course. How can I take the courses? If there's an order. But if I can't finish all the courses, and why would I not be able to finish the courses? If A depends on B, and B depends on E, then I can't take one before the other. Or if A depends on B, and B depends on C, and C depends on E, then I can't take any of them before each other. So in that case, that's a cycle. So what they're asking, the question is essentially asking, what is detecting there's a cycle in a topological sort? That's what this question is used to. Okay, so I think parallel courses is the same variation of some variation of topological sorts, except that I are taking it level by level. Then alien dictionary. Okay, so in this one, they are saying that there is a new language where they have a dependency of words. So this word is lexicographically smaller than this word. So this word here is lexicographically smaller than all of this, right? So they're kind of like trying to find a dependency. They're trying to find the order of the words. So from here, W and R are equal to W and R, but C and F are different. So that tells me that C must come before F, right? And that tells me that W must come before E, which is correct here. And that W must come before R, which is correct. So essentially, if you build a dependency chain or graph of all these words, and you run a topological sort or the letters that you can find. So from here, I know C comes before F. So if I put in my graph, C comes before F, right? And W comes before E. I'll build like a graph. And if I run a topological sort on that graph, I'll get my answer. Is that what? Let me see. It's what? I think, yeah, that's what this does essentially. So let me show this one. So essentially, you are building a graph here. Don't worry too much about it. I don't want to get the idea forward. So you build a graph here, and then you run a topological sort on the graph. So the reason why I'm saying this is because a lot of these problems, they look very difficult when you see them. But if you try to break them down to what they're actually asking for, the problem statement becomes simpler. The implementation might be difficult, but the implementation becomes simpler, and you have something to start with. So I think we are done for today. We are done for today. I think this is a lot. So I will stop here for today. And so just try and go through this sorting visualizers and try and, more importantly, understand the process behind solving the problems and how those sorting algorithms are using these processes and practice. Okay, thanks everybody.
Hello, can you hear me?
Yes.
All right. So thank you so much for that. It has been an amazing session. All right. Thank you so much for joining us. For those that waited to the end, thank you so much. Yeah. So I've dropped the feedback form for you to drop your feedbacks. It's very important also. So without further ado, we'll be calling it a day. This has actually been a very nice one. Also, you can find the link to the video on YouTube, which will be sharing the link much later. So in case maybe you missed something, so you want to go back to understand it more, then you can always say there. Thank you so much for your time. See you next week. Bye.
Right.